Okay. Okay, so I have started the live streaming. It takes a little bit of a time just to. Amish, Amish, I have to sit down. Okay. So, okay, so we are live now. So it's a pleasure to welcome one and all for this edition of the NSF Wednesday Colloquium. And it's a pleasure to have Professor José Gómez joining us from Spain for this particular colloquium. Unfortunately, we couldn't get him here under these situations, but hopefully he will also come to TIFR at some point. But for one and all who are new to the colloquium series, the Wednesday colloquium series actually is a platform that is as old as TIFR itself. It was a vision that was started by Professor Homi Bhabha, the first director and the founding director of the institute, who believed that it would be nice if all the natural sciences faculty members get together once a week and listen to an expert who is doing fascinating research in any contemporary research directions of physics, chemistry, or biology. That idea sort of has helped or enabled not only training wonderful graduate students at TIFR, but also enabled principal investigators within the institute to cross-collaborate, as well as, of course, start collaborations with the speaker who was to come to the institute on that day. So with that, of course, we have an eminent expert today, I won't waste more time. I'll actually let my colleague from the Department of Astrophysics and Astronomy and Astrophysics, Professor Gopakumar, to actually introduce Jose for this talk. Gopu.
Thank you very much, Jyotishman. It's a real pleasure and honor to introduce Jose Luis Gómez, popularly known as Jose to colleagues and friends. So Jose is associated with the Institute of Astrofísica Andalucía, that's in the beautiful town of Granada in Spain. Jose did his undergrad from Barcelona, moved to Granada for his PhD. Later, he went as a Fulbright fellow to Boston. I guess after that he spent a year in Manchester, moved back to Granada. He has been there forever. He and his army of students and postdoc are kind of working to understand in great detail black hole accretion, jet formation, especially in supermassive black holes, and using the best VLBI telescopes. And obviously, and he's part of the Event Horizon Telescope Consortium. And of course, he works for GMVA. And today you will hear about his explorations of this amazing telescope called Radiostron. So yes, and Jose, because of his leading contributions to EST collaboration, was awarded the Breakthrough Prize in 2020, I presume, for imaging the black hole, which we all heard about in great detail. And more importantly, these days, Jose is the leading proponent of next generation EHT, and he's a big supporter of Indian telescope participation in the network, especially in the Himalayas. And personally, we have been collaborating with Jose, and he has been helping us a lot in connection with this interesting black hole binary, OJ287. And with these words, I hand the stage to Jose. Thank you very much.
Thank you very much, Professor Gopakumar. It is for me a real pleasure and an honor to be giving this seminar in TIFR. So it's thank you very much for the invitation, and very much looking forward to continue with our extensive collaboration with Gopu and Loki and others. So let me then share my screen, and all right, let me see. Let's start the presentation. Okay, so today I'm going to discuss the sharpest view of Blazar jet that we can get with VLBI observations from space and also from the ground. So I will start with a general overview of blazars and supermassive black holes, and then I will go into some of the results we have been obtaining with space VLBI, and at the end I'm going to discuss a little bit the new results from the Eht Event Horizon Telescope, and as Coco mentioned, highlight the expectations we have for the next generation Event Horizon Telescope and amazing science that we expect to do in the next decade. So please feel free to stop me at any time if you have any questions.
José, can I stop you right now for just a quick thing? There are some things coming on your screen that you're sharing with us. The Zoom platform provides these image videos of all the participants. Could you just remove those? Yes, and then there is I guess,
yes. Let me.
There are a couple of things there actually.
Is it better now?
Yes, better. And then there is a floating meeting. Yes, gone. Thank you.
All right. Okay. Thanks a lot for letting me know. Okay, so let's start with an overview of what are blazars, what are active galactic nuclei. So, as you know, we believe that in most, if not in all galaxies, at the center we have a supermassive black hole. The growth of the supermassive black hole is connected with the galaxy evolution, and in some of these galaxies, we see that the core of the galaxy emits huge amount of energy. Actually, active galactic nuclei are the most energetic persistent phenomena in the universe. And how is this energy release? Why we have this huge amount of energy at the center of galaxies? And this is an animation that was made by Wolf and Stephen for a publication we did in Nature that shows the current idea that we have of how AGN works and how these amazing jets that we see extending from the center of the galaxy are produced. As you can see in this animation, we believe that at the center of the galaxy there is a supermassive black hole weighing of the order of millions to billions solar masses, which is creating a material leading to the formation of the accretion disk that you see here. And by some processes that we still don't know very well, the accretion into these supermassive black holes leads to the production of these huge, amazing jets that extend to sizes larger than the host galaxy, and are responsible for a huge amount of energy across the whole electromagnetic spectrum. So we have been the picture that we have got after many very long baseline VLBI observations of the sources is that we have this central supermassive black hole with accretion disk. Most of the X-rays are coming from the central portion of the accretion disk. We have also the VLR clouds, and then we have the jets. And we also see what we call superluminal nodes, and what we call also the VLBI core that I'm going to discuss in a minute. We see a stratification in the energy in the jet that goes from highest energies closer to the central black hole, 2 centimeter radio observations farther away. So for the past decades, for the last 30, 40 years, we have been observing these sources with VLBI. As you know, with this technique, we can get the highest angular resolution possible. And through monitoring programs led by the Mojave collaboration, also Boston University monitors, we have been studying these sources at this centimeter wavelength. So distances relatively far away from the central black hole, and studied the jet dynamics and understanding the physics of this object. We have determined that the jet is kinetically dominated and has a partially ordered field at these scales, and has Lorentz factors of the order of 10, and also through combination with multi-wavelength observations, actually in 2002, Alan Marshall and collaborator were able for the first time to establish the connection between the supermassive black hole and the jet. So we observed that when there is a dip in the light curve in X-rays, after that there is an ejection of a superluminal component in the jet that is traveling downstream the jet. So we clearly established this connection between the central black hole and the production of superluminal components, and also through multi-wavelength studies, we determined that in some cases, when these new perturbations, what we call components, or move along the jet, they interact with standing shocks, and they lead to a very high energy emission with energies all the way to gamma rays. So the picture we have established that there seems to be this recolocation shock located at about 10 to the 5th Schwarzschild radii from the center of the black hole. And after this is what we have been observing with centimeter VLBI. But of course, one of the most interesting parts is what is within what we call the VLBI core. How are these jets actually formed and accelerated? So we believe that the helical magnetic fields, either anchored on the black hole or in the accretion disk, are responsible for the launching of these jets. And also with the space VLBI observation, I think this already has an observation of 3C84 by Giovannini and collaborators, we have been able to actually get a glimpse of the jet formation. Also, there has been amazing advances in numerical simulations, and this is just one animation from Sasha Chekovskoy that shows that when we have a spinning black hole, it's possible to actually extract energy from the spin of the black hole and to power these amazing relativist jets. But so far, there are still many open questions to understand related to AGNs and black holes and jet formation. Among these, what is the actual magnetic launcher, whether it is a Blandford magic, so powered by the central black hole, or whether the helical magnetic fields that power these jets are anchored on the accretion disk. We need to understand how is this transition between the Ponting flux that it's the heat in our centimeter VLBI observation is converted into a kinetic dominating jet. So we need to also to determine what is the accretion rate, what determines also the jet power, what are the acceleration and collimation mechanism, and even we don't even know what is the jet composition and how the high energy particles that are traveling in these jets are actually produced. So there is, especially for the young students in the audience, that there is a new birth of this research field. So, in order to advance in these questions, what we need is to get polarimetric observations with even higher angular resolution, so we can probe the jet regions closer to the central black hole in a scales smaller than about 10 to the 4 Schwarzschild radii. So how do we do this? So with the technique of VLBI, it's possible to get a higher angular resolution by two methods. So one is that you actually observe a shorter wavelengths, and this is what we have been doing with the Event Horizon Telescope. And I presume everybody in the audience is familiar with the image of the central black hole in M87, which was only possible because we extended the wavelength of the observations with a grand array of telescopes all the way to just 1.3 millimeter. So obtaining this 20 microsecond angular resolution, which was not capable before. The other way is that we can increase the baselines of the VLBI observations and still do centimeter VLBI observations. But for this, of course, we need to have space VLBI observations. And I'm going to show you now a summary of some of the results we have obtained for the past decade on the space VLBI observations with the Radio Astron mission. This was a mission that was launched in 2011 and ended actually in 2019, but it has a large apogee all the way almost to the moon. So in principle, we could get an angular resolution up to 7 microseconds at the shorter wavelengths that could be observed with the radio astron 1.3 centimeters. So in principle, we could get angular resolution similar to what we are getting actually now with an Event Horizon telescope. So we started a key science program with the launch of Radio Astron, which was aimed to actually determine the jet formation, to study the magnetic field and how we can understand the jet formation and acceleration processes in Blazar jet. Here's a table of the summary of the observation we have been performing so far. So with our key science program, actually we collected more than 70% of all the imaging experiments of this space VLBI program. I'm going to give you just a very brief summary of some of these results, and then I'm going to get into a little bit more detail on some particular sources and latest results. So at the beginning, we started observations at L-band, so long wavelength observations, and we published the first paper in 2015, confirming the polarization capabilities of Radio Astron, and soon after that, we published the first Radio Astron observations in polarization at the K-band, that is at 22 gigahertz or 1.3 centimeter, which is the shorter wavelength that Radio Astron could observe. So this is in principle the highest angular resolution possible with Radio Astron and this space VLBI mission. And these are the images you can see here. We observed VLAC, and we were able to detect the fringes up to a projected baseline distance of about 8 Earth diameters, as shown here, which implies that we actually got an angular resolution of just 20 microseconds. And now it's very similar to what we are actually now getting with the Eht, but at a different frequency, so 10 times larger wavelength. And of course, at these wavelengths, these cores are still optically thick. And this is the advantage of using the Eht. The Eht observes these sources at 1.3 millimeter, and they are optically thin, so you can actually see the black hole shadow as we showed for M87. Nevertheless, with this observation, we were able to get these first 20 microsecond resolution observations in polarization, and we determined that we had a helical magnetic field in the core region, so very close to the central black hole, which is responsible to producing this.
Jose, this is Jyotish.
Yes.
Yeah,
Yes.
sorry, a quick question. Can you go back to the slide?
Yes.
Could you explain the images again? The one with the first polarization K-band observation. Could you just explain that image again?
Sure, of course.
How did you take that? And yeah.
Yes. So in this central image, you see in total intensity is shown in contours, and colors indicate the linear polarization, and the bars, I hope you can see them, indicate the direction of the electric vector. So this is the jet in VLAC, and we were able to get an image of the central region with the angular resolution of 21 microseconds. Then we combine these observations with other wavelengths, and we obtain this Faraday Rotation Map. The Faraday Rotation Map tells you what is the actual orientation of the magnetic field that we are observing. Because
so this is the magnetic field that you're imaging.
Exactly. So we were able to observe the magnetic field just in the vicinity of the central black hole, just at around 1,500 spatial radii from the central black hole. And through this observation, we were able to determine that there is this helical magnetic field, which is what you expect in the case of the jet being launched from the helical magnetic field anchored in the central black hole. In a minute, in 10 minutes, I'm going to show you the images of the polarization from the Eht. Yes.
So can I ask one more question? It's a very naive and ignorant question, I'm sorry, but the full width half max that you have shown has a unit that I don't understand. What is that unit?
21 microarcseconds. So this is 10 to minus 6 arc seconds. So to give you an idea, with this angular resolution, you can see a coin in the moon.
Okay, got it.
You can see a hair in this in the International Space Station.
Thank you.
Yes, thanks for your questions. Let me move to some other results. So then we also observed 373, and Gabriele Brun and collaborators, we published a paper in 2017, and we studied the brightness temperature on this source. We found an amazing change in the brightness temperature, which the brightness temperature is basically the amount of energy that you see in the core of the jet. So it's the higher the brightness temperature, the higher the emission concentrated in the smallest space in the source. So it gives you an idea of the huge amount of energy that these sources release. And then we also observed another very famous source, 0716 plus 714. And you can see here also the images. I'm going to go a little bit in less detail in these images, and then I will focus a little bit later on in other sources. But just to give you an idea that with these observations, for instance, for 0716, we found that there is a huge amount of energy concentrated in a very small space in the core of this jet, to the order of 10 to the 13 Kelvin. This means that I mean, we don't have actually an explanation for this huge amount of energy is concentrated in this small space, and we presume that this there are perhaps extra processes besides the synchrotron radiation we are seeing from these sources that may lead from time to time to this huge amount of energies being released. We also observed a prototype source, which is 36345, and these are L-band observations by Felix Polz and collaborator. In this case, these are 18 centimeter observations, but nevertheless, with the space VLBI, we got an amazing resolution of just 100 microarc seconds at 18 centimeters, so that about 10 times larger than what we usually get when we observe these with ground-based observations. And also more recently, in 2021, we had another look of 3673, Gabriele Brun and collaborators, and you can see here two different images at two different frequencies, and we saw that there is a significant stratification in the jet that was completely unexpected. We have not seen this before, in which high frequencies is basically the central spine of the jet which is emitting, while a longer wavelength is the jet edges that are emitting more. So this is telling us that there is a stratification in the jet that we need to explain with further simulations. And let me now go to OJ37, and this is one of the preferred sources from Professor Kumar. He is very much involved in these observations and participating in our observations, and for quite a number of years now. He has been also actively observing the source in the optical, and this is one of the most the best candidate actually for hosting a supermassive black hole. As you can see in the movie in the left, we believe that in the case of OJ37, we have a central black hole which is huge. It is one of the biggest, most massive black holes that we have detected so far, with around 20 billion solar masses in the center, in the primary. And we think that there is another black hole orbiting the primary, with about 140 million solar masses, and from time to time it crosses the accretion disk of the primary. And as you can see here in this movie, when the secondary crosses the accretion disk of the primary, this leads to accretion in the secondary and a flare in the optical. So we have been monitoring the optical light curve of this Blazar for almost a century now, and we see this double peak in the light curves, and Kumar and Mari Valtonen and collaborators, Loki Day, they have been modeling this binary black hole system, and they have found that in order to explain this light curves, and we need and this supermassive black hole binary with a quite eccentric orbit, with a separation of the other 26 microseconds. So if you remember, this is more or less of the order of the angular resolution we are getting with the Radio Astron and with the Event Horizon Telescope collaboration. And these are very, very well known to the Blazar. It has been observed with VLBI for decades. And for instance, here you can see a plot of how it changed the jet ridge line. So we have seen that the jet in this source seems to be swinging with time. So it's changing the direction in which the jet is being ejected. And Loki and GoPro and collaborators have been modeling this change, as you can see in this plot, over time using this binary black hole system. And actually, this has been a very successful model. So it does seem that the precession produced by the binary system may explain the changes in the orientation of the jet that we have seen over time. So we have observed this with Radio Astron, and these are the observations. We get amazing detections, and these are the images we obtain at different frequencies. With different imaging techniques. So you could see here image with angular resolution of the order of 103 microseconds, one resolution of the order of 60 microseconds, and the highest angular resolution we could get, which is of the order of just between 10 and 20 microseconds, showing the innermost part of the jet. When we study this jet and what is the orientation of the jet, we find that there is a systematic or progressive bending of the inner jet with increased angular resolution, which is what we actually expect in the case that we have a highly twisted jet that is the result of appreciation due to a binary black hole system. So we have also studied, other properties of the jet, determining the magnetic field and the strength and also the orientation. We also did this Faraday rotation analysis that I showed that in this case, as shown in this image, there's a stratification in the Faraday rotation across the jet width, which can be interpreted as being produced by a helical magnetic field. So with these observations, we have been able to pin down that there seems to be this helical magnetic field that we saw at the beginning in the GRMHD simulations that is launching these huge jets. So this is, as I was mentioning before, this is a particularly interesting source for many reasons. I mean, if we confirm that this is a binary system, it could be one of the best targets also for looking for nanohertz gravitational waves. So understanding this system is particularly important, and since 2017 we have been carrying out a monitoring program that includes observations with the Event Horizon Telescope, GMV plus ALMA, and Radio Astron. So we can combine observations with quite more or less similar angular resolution at different frequencies. And this is very important because when we combine these images at different frequencies, we can get this information about the jet properties, the magnetic field strength, and how energetic are these particles responsible for the emission. And we have been doing, as I mentioned before, since 2017 with observations every year. In 2018, we also observed with the EHT. Then we stopped observing we did not observe with the EHT in 2019 and 2020 due to the pandemic. But we have resumed observations this year. And actually, just a few weeks ago, we ended up at the Event Horizon Telescope campaign for 2020. And we all observed against OJ27. So besides these observations are radio wavelengths, a radio continuum, we have also observations at different energies, also observations in the optical, ultraviolet, X-rays, and gamma rays. So the idea is that we can't perform a study of how the jet in this particular interesting source changes with time, with the main goal of confirming whether this binary supermassive black hole in the system. And besides this, to determine what is the strength of the magnetic field and to study jet formation in this source. And this, I'm going to show you just a summary of some of the observations that we obtained with an array which is called the GMBA plus ALMA. This is a global millimeter VLBI observations at 3 millimeter. So the Eht Horizon telescope observed at 1.3 centimeter, and this array observed at 3 millimeters. So we get an angular resolution which is a little bit like 3 times worse than the Eht Horizon telescope, but nevertheless we are getting something like 50 microsecond angular resolution, so, which is really quite amazing. And actually in 2017 was the first time in which ALMA participated. That marked the first Eht Horizon telescope observations with ALMA and also with this array operating at 3 millimeter. I'm not going to get into the details about what you are seeing in this plot, which shows the spatial coverage of the VLBI observation that gives you an idea of the angular resolution you may get. And in particular, in this plot, I wanted to show that with the first participation of ALMA, we could extend the angular resolution in the north-south direction by a factor of about 3, which is very relevant for this source. Let me show you here the images we got from 2017 observations. And for this, we have used different imaging techniques. We use the regular clean methods, and we use now the methods that we are using in the Eht Horizon telescope for the first time to a different VLBI observations. And we use the script that we call Eht and the other script SMILE. And you can see that with these new algorithms that were developed for the Eht Horizon telescope, we can actually over-resolve the source. We can get an extra angular resolution as compared with the observations with analysis of the imaging being performed with the method, the clean method. And when we focus with this over-resolve or extra angular resolution that we get with RML, we did find that in the case of this jet, there seems to be a bending in the jet. There is an agreement with a jet intersection seen in projection. And most interestingly, also, we observe Eht polarization. And in these observations, you can see here, the bars indicate the direction of the electric vector that we observe. So the inferred magnetic field is perpendicular to the electric vector that we are seeing here. And therefore, the magnetic field has a predominant component which is perpendicular to the jet. So this suggests that we have a predominant toroidal component and most probably a helical component as we are expecting for the acceleration of these jets. And this component here, that with the usual methods we could not resolve out, but in this method we see like a V shape with different magnetic field configurations. And through analysis, I'm sorry, that I'm not going to get in detail. Now we believe that this is due to the existence of a recollimation shock in this location in the jet. These recollimation shocks are also important because, as we discussed at the beginning of the talk, we think that there are some components on some higher density regions in the jet that we call components moving downstream, and some of these components interact with the standing shocks, and these are recollimation shocks produced by a mismatch between the pressure in the jet and the external medium. And it is the interaction between these moving shocks and the standing shocks what produces extra energization of the particles in the jet and leads to very high energy emission all the way to gamma rays. And we may think even to TVs, and in some cases we are now seeing some connection between the neutrino detections and Blazar activity. So they may be produced in these regions. So how do these observations with a ground array at millimeter wavelengths at 3 millimeter compare with previous radioastron observations? And these are the two images that we have seen before. This is a radioastron image we took in 2014, and this is the GMBA plus ALMA, so ground array at 3 millimeter. in 2017. And you can see that there has been some changes. So we see that the brightest component is actually downstream the jet, but you can see that there is a significant change in the orientation of the jet with time. So in these 3 years, the orientation of the jet seems to have been changed by about 60 degrees, rotated clockwise in 3 years. So we are now in the process of analyzing the observations taken at different epochs, and we are seeing that indeed there seems to be a change in the orientation of the jet. And we have been comparing this with the model that Loki Day and Gopakuma have been developing for this method, this source based on a supermassive binary black hole system. And you can see here in red, I'm plotting the orientation that we are measuring in our VLBI observations, and in green are previous observations, red are these new observations, and in blue you can see here the prediction from Loki, Day and collaborators using the binary black hole model, and you can see that it is the agreement is really nice. So it does seem that what we have a binary supermassive black hole system in OJ27. So let me now move to other observations and other results obtained from a ground array millimeter VLBI observation, and in particular observations from the Event Horizon Telescope. And as you can see here in 2021, so last year, we published also the first observations with the Event Horizon Telescope of CNA. This you can see the amazing image in which we see the actual collimation profile of the jet as shown here. So we are now probing how these jets are actually being collimated and accelerated. In 2020, we published also the first Event Horizon Telescope observations of one of the most energetic blazars that we know, which is called 3C279. And you can see in this image a composition from the images obtained at different wavelengths. This is a ground array 7mm observation. Then when we observe a 3mm, we increase our angular resolution. So we zoom into the inner region of the jet. And with the Eht at 1.3mm, we zoom all the way in with our angular resolution of about 20 microseconds. And we found that the actual core at the beginning of the jet seems to be elongated. And we found also some really quite complex inner motions in this jet. And we have been also observing this source with the space VLBI, with the radio astro. And let me show you how do they compare. So this is, as you can see here, this is the Eht 1mm observations. So we observed with the radio astron, and these are the observations that we observed and UV coverage with an angular resolution of the order of about 20 microseconds. And these results are that I'm showing you now are actually being now reviewed in Nature, and we hope that it's going to be accepted. And let me show you quite an amazing image that we got with radio astron. But before that, let me show you how do this image compare with previous observations. So to the right, you can see the jet 3C279 observed with at 7mm of 43 gigahertz with the Boston University monitoring program. In the central image here, you can see the Event Horizon Telescope. So you can see here the tiny little section, and they are actually shown on exactly the same scale. So this is what the Eht observes, and this is what the VLBI 7mm observes. So the whole thing of the Eht is just within what we call the core. And of course, with the ground array, we just see a blob. We just, a Gaussian, we don't see anything else. We were able to see this with the Eht. And now, this image that you see here is the actual radio astro observations. Note that this is 22 gigahertz, but with the same resolution as what we got with the ground array at 7 millimeters. And you can see the similarities are, almost the same image, very similar. We do see changes in the brightness of some components due to change in opacity between the 22 gigahertz and 43 gigahertz. And again, the teeny tiny little EHT image. But the actual resolution from the radioastron is not this one. So this is with, just degrading the resolution just for comparison with previous observation. But when we actually put the radioastron glasses, when we get the actual image that we got from this source, this is what it actually pump out. So you can see that what we saw here, we could not resolve anything across the jet width. Here we have been able to resolve and see these filaments that I'm going to discuss in a minute, and how this image actually compare with the EHT. And now you can see the similarities. We are getting images with similar angular resolutions, and so we can see compare that this is the core, this is the first component that was seen in the EHT. But since we had more than the 20 antennas on the ground, then we can see the rest of the jet that was actually blind to the EHT. And as you can see here, we see these filaments in the jet. I'm not going to get into the details about how we did the image, but let me just get into these filaments that we observed. So in this composite image, you can see here again, EHT image is shown here, radioastron is shown in contour. For comparison, this is the 7 millimeter image, and this is what we saw with radioastron. So, and we found these filaments. So the jet is just not a funnel. So they are actually filaments within the jets, and we were able to fit the filaments, and we saw that there is a periodicity or spatial periodicity of about 175 parsecs projected. And we studied different possible sources for these filaments that we see in the jet, and we discarded many of them. And we believe that Kelvin-Helmholtz instabilities, which are associated to the fact that we have fluid propagating through the ambient medium, this leads to also to some jet instabilities, and this create pressure waves in the surface of the jet that leads to these filaments with a significantly higher brightness. So we were able to model these, and we were able to determine that the Mach number of the jet should be larger than 10. And we also put an upper limit for the Lorentz factor of the jet of 20. And we also studied the polarization. In this image, you can see here, this is the total intensity. And in this image to the right, in gray, we see the same image as we have here in color, so total intensity. But now the sticks that we see here indicate the direction of the electric vector. The length of the sticks indicated the intensity of the linear polarization, and the colors of the sticks indicated the degree of linear polarization. So in summary, what we see is that the electric vector seems to be following these filaments, which is an agreement with being produced by Kelvin-Helmholtz or instabilities, and also by the fact that most of the emission is in one side of the jet. So you can see here the green filament is significantly brighter than this other filament here, than the red filament. So this tells us that there should be a helical magnetic field, and we were able actually to determine that the magnetic field is rotating clockwise, as seen in the direction of motion, and the intrinsic pitch angle of the helical magnetic field is around 45 degrees. Of course, when we see this in the observer's frame, we Lorentz transform this, and we see a mainly toroidal magnetic field, as we can see here. So this provides a really beautiful overall picture of the source. And as I said, this is now being referred for publication in Nature. So let's now go back to the EHT, and in the last section of the talk, I'm going to discuss a little bit the results we had from the EHT, and most interestingly, what do we expect in the future. So I believe most of the people in the audience have already seen this beautiful ring associated with the black hole shadow that we detected and published in 2019 from observations of M87. And as you can see, this is the regular VLBI jet that we see, and with the HT we were able to actually detect this. But more recently, last year we also published the magnetic field. So we published what is for the first time the magnetic field in the vicinity of the central black hole, and these are the polarization images at different frequencies, and this is actually the Eht polarization image, which is summarized in here. As you know, in 2017 we observed Eht in 4 different days, and these are the images we observed we determined for 4 different days. In this hairy plots, you can see that this indicates the direction of the electric vector, which is also indicated here in the bars that we show here. So we see that the electric vector is twisted around the event horizon of the central black hole in Eht. And through also comparison with relativistic MHD simulations, we were able to determine that the magnetic field is predominantly poloidal and has a strength of around tens of Gauss. With a comparison with a library of MHD simulations, we rule out that the case of a Schwarzschild black hole in Eht. So we have a spinning black hole in Eht, and also we determined that the accretion is in a state that we call a MAD state, which is a magnetically arrested disk. So you have to imagine that this accretion disk that we saw in the first movie at the beginning of the talk. So these are these accretion disks around the central black hole, and the magnetic field in the accretion disk has a predominantly poloidal component, but it is actually the energy stored in the magnetic field is larger than the one stored in the particle. So the magnetic field actually dominates the dynamics when all the material is actually being fed into the central black hole. So in some cases, the magnetic field is so large that it's arrested or stops the accretion of material into the central black hole, and this is what we call magnetically arrested disk. So it stops the accretion, and in some of the material just follow the poloidal field lines and get accreted into the central black hole. But it is the magnetic field most probably anchored in the event horizon of the central black hole, which is governing the accretion and the production of the jet in Eht. So amazing results. Magnetic field for the first time observed in the event horizon, just in the vicinity of the central black hole. But we want to do more. So this is amazing. Of course, everybody is expecting the results from the Eht in the observations of the galactic center. We will publish this soon. I cannot give you more details, but it's going to be soon. And but after that, we want to even improve our array. Okay, so we want to get even higher resolution and higher dynamic range, so better quality images in our event horizon telescope observations. And this is why now we are designing, as I hope to mention at the beginning of the talk, what we call the next generation event horizon telescope. So the idea is that we will this will be in phases, 2 different phases, and we want to add about 10 more dishes to the array. And we want also to expand, the bandwidth observations and increase the data volume of the data to amazing values of the order of 100 petabytes. So we are going to get a lot more data with this observation, and of course, we will get significantly better images and with significantly higher dynamic range, as I'm going to show in a minute. So we are in the process of designing this new array, and as you see, we expect that by 2014 we will end up with the design and then the construction phase, and by 2025, 26 first observations, and then a full array by the end of the decade. And there are many places where we are now studying where to locate these new dishes. And as Gómez was mentioning, of course, having one dish in India would be really excellent. This will be an amazing site, very high with very dry. So this could be an excellent addition for the next generation Event Horizon Telescope. The good thing is that now we have really very sensitive array, very sensitive antennas in the array. So we have Phase ALMA, and we have the large millimeter telescope in Mexico, and we have also Phase NOIMA in France. So we have really three big dishes, especially Phase ALMA. So even with a smaller dish of the other just 6 meters, we can do amazing things. So what do we want to do? So in the first observations or with the HT, we were able to get the first image of a black hole, and we were able to verify GR with a precision level of the order of 10%. And why so? So I think that the explanation is quite clear in this movie that you are seeing now in the lab. So you see here the black hole, you see the photons going around the black hole, and then this produces what we call the N0 ring. Then there are some photons that actually go around the black hole. When they go around the black hole, they produce a thinner ring, which is what we call the N1 ring. And there could be also another photons that actually go twice around the central black hole. And as you can see in this movie, when we have this, we have a significantly thinner N2 ring around the central black hole, as you can see here. The image we got from the HT is a combination of all of this. So we see mainly the N0, which is all the material around the central black hole, and this N0 is mainly determined by the astrophysics. So the precision that we get for a certain GR is of the order of how we can actually measure the astrophysics around the black hole, and this gives us this 10% accuracy. But if we are able to get the rings in N1 and N2, especially at different frequencies, because it should be achromatic, then we can actually test the GR with, in the sound field regime with a precision that has never been able before. And actually, just by checking the circularity of this N1 or N2 ring, we can even determine not only do this test of GR, but also even determine the spin of the black hole, because the circularity of this ring is determined basically by the spin of the black hole. So this is one thing that we want to do. And of course, we want to make movies. We took the first image of a black hole, but we want to actually get the first movies of black holes. And this is what it is shown in this slide. So in the left, you can see a simulation. In the center, you can see the blurred, this with the spectral resolution. Here you can see the UV coverage. And to the right, this is the reconstruction that we will get from the next generation Event Horizon Telescope. So we will be able to see on real time how black holes actually accrete and how black holes produce this amazing jet, but how energy from the central black hole is being actually extracted. So, and here you have another example of the kind of image fidelity we will get with the next generation EHT. And this is for the case of M87. This is a simulated jet of M87. And this is the expected imaging that we will get in the next generation EHT. So as you can see, we will be able to see not only the ring, but also the whole jet. So we will be able to make also movies, as shown here, of M87. On the left, you see the GR EHT simulation, and on the right is actually the expected reconstruction from the NG EHT. So on real time, we will be able to see how this, for the first time after decades of observations, how energy is extracted from central black hole and these jets are being produced. So I encourage everybody to join the NG EHT. The next generation EHT is an open collaboration. It's open to everybody. We have now formed different working groups. We have working groups devoted to fundamental physics, to study black holes in the Gómez context. jet launching, accretion, transients, and new horizon, and new algorithms, and so on. As I said, this is an open collaboration, and it's open to everybody that will be willing to contribute. And among one of the things we want to study is indeed supermassive binary black hole systems, and of course the dilemma of, or what is called the final parser problem, which is, I mean, how do you remove angular momentum from two colliding supermassive black holes before they start to meet gravitational waves that will shrink the orbit? And so this is a well-known problem for a long time ago. So we do expect to dig up into solve to understand better this. But the most relevant will be also the most relevant study will be the connection between these supermassive binary black holes and the detection of nanohertz gravitational waves that we expect to see this very soon with pulsar timing arrays included in the Indian pulsar timing array, and I'm sure that Gómez will be very happy to further discuss this during the Q&A. And this is just a summary of the talk. And so as you have seen, with space VLBI observation and centimeter wavelength and ground-based millimeter VLBI observation, we are getting a better understanding of what are the accretion process in supermassive black hole and jet formation, and the future is really bright for the young students. I mean, when in this decade we expect to get the first movies of supermassive black holes, and we are right now developing the next instrument, which is going to be really revolutionary in our understanding of black holes. Among the key science goals of the next generation EHT will be to perform the GR test of the current metric really at the horizon, to understand how energy is extracted from central black holes, to understand this accretion. We also understand black hole demographics and how supermassive binary black holes coalescence and to produce gamma ray, gravitational waves, and how supermassive black holes grow over time. The connection with the multi-wavelengths and also the production of very high energy, including neutrinos, IgM populations. So there's, as I said, there are different working groups, and the future is really bright. So, and let me just finalize the talk with this slide. You have here a link that you can use for just participating in the NGEHT. You will be directed into provide your information, your personal information, and which working groups you may be willing to participate. As I mentioned before, we have many different working groups devoted to different aspects of the science goals that we would like to achieve with the next generation EHT. So I encourage people to sign in for participating in this. We are now actually starting to draft the white papers that will guide the science goals for the next generation EHT. And let me also advertise the meeting, the next generation Horizon Telescope meeting, the first actual face-to-face meeting that we will have on the NGEHT, and that we will be hosting here in Granada, Spain, at the end of June. And here's also a link in case you would like to register and participate in this. As I said, it's fully open. We are mostly, we are really eager into getting new people contributing to this, especially early career people. And in the meeting, we will have also a joint day together with the Eht Horizon Telescope. So we will discuss the connection with the future science that we want to do with these arrays, and I encourage everybody to participate. So thank you very much, and I'm very happy to take any questions.
Thank you very much, Jose, for a very elaborate presentation and perfectly on time. So there is lots of time for discussion and questions. There is already one person who has raised a hand. Preeti Kharb. Preeti, could you unmute?
Yes. Hi, Jose. Preeti here. So excellent talk. I mean, there were fantastic images, especially through 279 with those filaments, which reminds us of the M87 filaments that we saw. My question was about OJ287 actually. So in your 2017 April image, I just wanted to know where is the core in that image and if you see any counterjet emission.
Yeah, that's actually an excellent question, and we think that the core, as you can see here, it is this region here. This is the upstream end of the jet, but actually the brightest region is around here. So, but as you know, with the VLBI observations, we lose the registration of the image. So we really don't know, I mean, the absolute position of the image, and therefore we are not sure about what is the actual beginning of the jet. But we think it is this region here, and especially because I'm sorry I cannot show you the Event Horizon Telescope images that we took of OJ287, but I can tell you that when we compare this 3 millimeter with the 1.3 millimeter observation from the HT, spectral indices analysis indicate that this region here, so the upstream end here is the beginning of the jet. So if there is a supermassive binary black hole system, it is right here. It is located around here. And we did not detect that in these observations. But we are also limited in our dynamic range. So it may be that the secondary is there, but it's too bright, or it was too bright, sorry, too dim when we took the observations. But if there is a binary system, it should be around here.
I see. So then, do you actually see counterjet emission here?
No. You may see a little bit of emission here, but I think this is a little bit of an artifact from the fact that the coverage is not very large. So, but we did not see any evidence for this, and we have not seen also evidence for a secondary jet. But this is something that in this paper that we just it's also been, well, now it's basically accepted. This is also something that we comment in this paper. We with these images, with the limited dynamic range that we have, we do not see evidence for a secondary jet, and we did not have enough angular solution in dynamic range to actually partially resolve a secondary.
Got it. Okay, thank you.
Thank you, Preeti. Questions from Zoom or the audience here? Okay.
I will wait for if others are there, even in YouTube or. Yeah. Fantastic talk, Jose, as usual. So it's really a tour de force. So many amazing results, and this is how your group operates these days. So I have a couple of questions. This is especially on that. So this is about the NGHT. Something interesting is there. I mean, so it's going to be dual frequency, but I realized that some of the small stations, see, the numbers can be different. So I presume that's because of the location may not be appropriate for both, 230 and 345 gigahertz. Is that the idea? Yeah, that's an excellent question. Indeed, yes. So we are now searching for the best places, best locations at which we could hopefully also observe with 345. And as you mentioned, we are now developing the receivers that are going to be simultaneous at 230 and 345. So in many of these new locations, we expect to be able to observe also at 345 gigahertz.
not in all of them, but for instance, if we have an antenna in the Himalayas, I do presume that it's so high and it's so dry that it would be, an excellent site for 345 observations. So in this case, with these higher frequency observations, we expect to get even higher, something like around, perhaps 50% higher angular resolution than what we are getting with the EHT, which means that we will be able to get observations with an angular resolution of the order of 12 to 15 microseconds. This will be absolutely essential for observing other supermassive black holes shadows, not only in Eht and hopefully at the galactic center, but in other sources. This will be like a new window for population studies of accretion in this and to understand the black hole growth over time. If we can get accurate measurements of the black hole mass and the spin in other sources other than the Eht and the galactic center. So this will be really key. And for the case of supermassive binary black holes, I most probably with an array of 345, if there is an actual binary system in Object 27 and the secondary becomes bright enough, at least during the crossing through the accretion disk of the primary, that may lead to further activity in the secondary, we should be able to actually spatially resolve the two of them and to follow the orbit of the two of them. And with the orbit, we can get, of course, a much accurate determination of the masses and so on. So this will be really key. And why we will be able to do this with smaller dishes? As you know, the EHT is based on relatively large dishes that operate regularly at millimeter wavelengths, single dish observations. But the fact that we have these 3 anchor stations, phased ALMA, LMT, and phased NOEMA, this implies that we can actually use smaller dishes. And that even with a 6-meter dish, we think that we will be able to get the good data to actually be able to get a significantly better UV coverage. So we will be able to get an UV coverage like this, which, an instantaneous UV coverage that will be able to actually get the movies of the galactic center that we expect. So it's going to be very, very important.
Yeah, thank you very much. I have one more question. Yeah. So this is, especially for that 3C279, that's amazing, right? So obviously everybody uses this as a calibrator, but what I was, the kind of a resolution, yes. So the 2 jets, tiny thing can be resolved by EHT, but then with the radioastron, actually see everything, and this kind of so-called periodic motion. Is that the reason? When these things were not resolved, there was a suggestion that 3C279 can actually host a supermassive black hole binary. I vaguely remember this, right? So when
I remember that, but to be honest, Gómez, I don't remember now why it was discarded. But yes, it was actually suggested that it may have been a binary black hole system. And maybe that these filaments may be produced by 2 different black holes or things like this. But at least when doing the modeling, it does seem that we cannot, in a very coherent way, explain these filaments using this model of Kelvin-Helmholtz instabilities. But let's see. Perhaps in the future with better angular resolution, we may get a surprise and see that there is a binary system there as well.
Yes, thank you. One more, the last one. After I'll keep quiet. So there is an angle which you have not really just briefly mentioned, right? So this neutrinos thing, right? This is something Yuri was kind of mentioning that, you know, they're picking up new events which they're keeping quiet for the time being. And of course, the political scenario is also problematic. So that is actually, you know, with the new things coming up, you know, in Lake Baikal and other places. So this is going to go up, and you know, the real confirmation that AGNs are indeed factories for this fantastic, you know, new astronomy, and I think, yes, Yuri is the only person in our collaboration talks about those, but you know, this will go up like equally interesting like gravitational waves from a different bunch of people. I mean, so this is something, and many of your magnetohydrodynamic simulations will be crucial to sort of explain the observed energy ranges, and you know, all those things, the rates and everything. So that's an amazing opportunity in the coming years. So
yeah, absolutely right. Yes, this is we are very actively working on this research line in the next generation Horizon telescope, and it could open you know, a new window into how these neutrinos are produced. We think these are produced by the extremely high energy protons, but how you get these protons accelerated to extremely high energies is still unknown. And we do expect that with the NGEHT, we will have enough angular resolution to actually locate where maybe the site in which these high energy protons are being accelerated. And probably we will get new physics there, because we have not a clear idea of how you can accelerate protons to such high energies. So it have been suggested that you may have you know, magnetic reconnections. So it may be, but you are expecting this more near the accretion disk, and we don't have the angular solution for a second disk yet. So I think this would be indeed really an excellent, you know, new field, new research line associated with these truly amazing sources.
Yeah, thank you very much. So in our 60s, Jose, we all will be very busy reading papers. You know, there will be so many things to understand, and the youngsters will take over. So with those words, I'll hand over to.
Yeah, thank you very much, Gopu. Thank you for actually having Jose here, inviting him, and you know, making sure that he gets invited. Are there any other questions from the Zoom audience? If there are none, let's actually thank Professor Jose Gómez once again with a big round of applause from the auditorium. And from actually, I hope the Zoom audience can hear me, so maybe you can unmute yourself and just do clapping. That would be great. It's just is a sort of a thing that you miss in online colloquium. You don't hear the loud applause at the end.
This is something that I miss, really. And the chatting with the people after this. Yes, this is the most fun part.
Yes, and please do come to TIFR whenever you get a chance, when things normalize a little bit more for international travel. And just wanted to say that this colloquium series, actually, the talk ends usually with the speaker walking with the audience to have some tea and snacks. Unfortunately, the tea and snacks are here, but you are not. We are going to enjoy that and discuss your talk a little bit more. So thank you very much for being with us.
It was a real pleasure. Thank you very much again for your invitation. It was a pleasure and an honor to give a talk to you. Thank you.
Thank you. Just wanted to tell the Zoom audience, thank you for staying by. And next week, we have Professor G. Ravindra Kumar, a member in TIFR itself, one of our own, who is going to talk about high intensity lasers. Okay. So please stop by physically in the auditorium and not just join by Zoom, because he will be actually here and giving a talk, a colloquium. I would also want to thank the auditorium staff today. We had a very difficult time, Jose. Our institute network was not cooperative at all. and we actually started your talk in the auditorium on YouTube. Luckily, I had made you a co-host. We had lost connection for almost like 5 to 10 minutes. So now we gained back, but everything is on YouTube. So thank you, Jose. Thank you very much.
Thank you. Okay. Bye-bye then.
Bye-bye. Yeah.
Thank you very much.
Bye.